Ever stop and wonder how your phone can find one specific contact in, like, a split second? Or how a map app just knows the fastest route through traffic? Well, the secret sauce is a set of powerful, invisible instructions that are basically running our digital world. So let's pull back the curtain on these secret rules. Picture this, and hand you a massive phone book with millions of names, but they're all jumbled up, totally out of order. And I tell you to find John Smith. I mean, where would you even start? This is exactly the kind of problem computers are solving all day, every day. And how they do it, it's pretty fascinating. You see, at their heart, all these super complex tasks really boil down to some pretty basic problems. Problems like searching for a piece of information or organizing a messy pile of it into something useful. And for every single problem, computer science has a strategy, a recipe for solving it. And that recipe? That's what we call an algorithm. Now, this isn't just a friendly suggestion. It's a super precise step-by-step set of instructions. Think of it just like a cooking recipe. You follow the steps exactly, and you're going to get the same result every single time. This idea is the fundamental building block for, well, everything we're about to talk about.
All right, let's get back to our phone book problem. The first big job for an algorithm is often just finding that needle in a digital haystack. So how do we actually write instructions to search for one specific thing?
Well, the most obvious way to do it is to, just start at the beginning and check every single thing. It's not exactly elegant, but hey, it's a strategy. Programmers have a great name for this, the brute force method. In more technical terms, what we're talking about is a linear search. You just line everything up and you check each item one by one in a straight line until you find what you're looking for. Pretty simple, right? The steps couldn't be more straightforward. You start at name number 1 and you ask, is this John Smith? Nope. Okay, on to name number 2. How about this one? And you just keep going like that until you finally get a yes, or you just run out of names to check. And this is where we see the big trade-off. This quote here really nails it. This method is generally pretty slow. I mean, can you imagine if John Smith was the very last name in that phone book of a million names? He'd be there forever. But on the flip side, if he happens to be, say, the third name, well, then a linear search finds him almost instantly. It's all about luck. Of course, we can't just cross our fingers and hope to get lucky every time. For a list with millions or even billions of items, checking one by one just isn't going to cut it. Which leads us to a really important question. How can we be smarter about this? And this table here perfectly illustrates that smarter way. It's called a binary search. Look at the difference. While the linear search just kind of plods along one by one, the binary search uses this clever divide and conquer strategy. But, and this is a huge but, look at that first row. It has one critical requirement. The list has to be sorted. That's the key. So how does this magic work? Okay, instead of starting at page 1 of our now alphabetized phone book, you crack it open right to the middle. Let's say you land on the name Miller. You're looking for Smith. Right away, you know Smith comes after Miller, so you can literally just ignore the entire first half of the book. Boom, you just got rid of 500,000 names in a single step. Then you just do it again with the half that's left, and again, shrinking the problem down like crazy fast. So we've established that binary search is incredibly fast, but it's totally dependent on that one little detail. The list has to be sorted. This brings up the next logical question, right? How do we even get a sorted list to begin with? How do we take a chaotic mess of data and tame it?
Well, you guessed it. Just like with searching, there are different algorithms for sorting, and each one has its own unique strategy. We're going to look at 3 common ones: bubble sort, insertion sort, and merge sort. Let's do a quick flyby of how each one works, and maybe more importantly, why you'd pick one over the other.
First up, we have bubble sort. This one is probably the easiest to understand. It just kind of shuffles through the list, comparing 2 items right next to each other and swapping them if they're in the wrong order. The bigger items bubble up to the end. The catch? It's really simple to program, but oh man, is it slow for big lists. It's a fantastic teaching tool, but you're probably not going to see it running your bank's software.
Next is insertion sort, and the playing card analogy here is just perfect. Imagine you're dealt a hand of cards. You pick them up one by one and insert each card into its correct spot in your hand. That's exactly what insertion sort does. Its real advantage is that it's super efficient for small lists. Or, and this is cool, for lists that are already mostly sorted, it can tidy things up real quick.
And finally, we've got merge sort. And hey, look at that phrase again, divide and conquer.
This algorithm takes a huge, messy list and just breaks it down and down and down until you have a bunch of tiny lists with only one item each, which by definition are sorted. Then it cleverly merges all those tiny lists back together in the correct order. This one is an absolute workhorse. It's a bit more complex, but its performance is so reliable and efficient, making it a favorite for tackling massive, chaotic datasets.
So, we have all these different ways to search and all these different ways to sort. Why all the options? Well, because in the world of computing, the strategy you pick has absolutely massive consequences, especially when you're wrestling with huge amounts of data. Just look at this. This slide really says it all. To find one item in a list of 1,000,000, a linear search in the worst-case scenario might take 1,000,000 steps, 1,000,000. But a binary search, by cutting the problem in half each time, it would take about 20 steps. Not 20,000, just 20. The difference isn't just big, it's staggering. Efficiency isn't just a minor detail, it's the whole game.
And that brings us to the most crucial point of all. These two ideas are totally linked. To unlock that unbelievable speed of a binary search, you first have to put in the work to organize your data with an efficient sorting algorithm. It's a classic trade-off, right? Do the work up front to sort the list, and you will save an incredible amount of time down the road.
And look, this isn't just some abstract computer science theory. These exact principles, searching and sorting, are running quietly in the background of your life every single day. They're what make all the impossible-seeming things our tech does feel totally effortless.
Seriously? Every time you see a sorted list of emails, get a movie recommendation, or just find a file on your computer, algorithms are doing the heavy lifting. So the next time you use your phone or your computer, just take a second to think about those elegant, invisible instructions that are sorting, searching, and basically guiding your entire digital experience. Kinda makes you wonder, what rules are really running the show?